in understanding a little bit about cross-site request forgery. Right. All right. Let's spend some time in understanding a little bit about cross-site request forgery, or CSRF in short. CSRF is a security vulnerability that is commonly overlooked. Until about 2017, it figured in the OWASP's top 10 security risks list. And only recently it got removed from the list owing to better tooling support that exists today to mitigate the problem. We'll first try to briefly define what CSRF is all about. We'll look at the threat model, some of the defense techniques to solve that. We'll also discuss briefly about a special form of CSRF called login CSRF, and finally we'll wrap up with a demo. CSRF is an attack in which a victim is tricked into performing unwanted actions on a trusted site when the victim is already authenticated. Let's look at an example scenario. The victim logs into a trusted site, in this case, a bank. Upon successful authentication, the bank establishes a session and returns the session identifier in a setCookie response header. The browser saves this session ID in a cookie, and all requests going forward to the bank would include this cookie. This is all fine and dandy because the user does not have to supply the authentication information with every request going forward. Now let's suppose the victim also visits a third-party web page that happens to have the CSRF attack code. In real world, this step would involve some form of social engineering where the attacker would lure the victim into loading such a page. The CSRF attack code in this case consists of a form that auto-submits itself to the bank. It has the parameters that would enable the transfer of funds from the victim's account into the attacker's account. When the browser sends this request, it would also include the cookie associated with the site bank. When the bank gets this request, it would think that this is a legitimate request and execute it. I want to highlight that the gist of the problem is in the browser sending the cookies for all requests associated with bank, and bank being unable to distinguish between legitimate versus malicious requests. One of the recommended strategies for fixing this is via usage of tokens. A token in this context is a large pseudo-random value that is included along with the request and later validated on the server side. Let's look at the scenario again. The victim logs into the bank. Now, in addition to creating the session, the bank also creates a CSRF token and returns this to the client. All requests from the client are expected to include the CSRF token, and it is the responsibility of the server to verify the validity of the token and reject the request if the token is invalid. Now, when the request from the attacker comes by, since the attacker has no way to supply the CSRF token, the request will be rejected. There are a few ways in which you can manage the token. The pattern that we just saw is called a synchronizer token pattern. This is where you maintain the state information on the server, the state information as to what user session has associated with it, what CSRF token. There are a couple of ways in which you could do this without using server-side state management. With encryption-based token pattern, you would use a key on the server to encrypt the user ID, timestamp, and unknowns, and use the resulting value as a token. When you get the token back from the client, you would use the same key to decrypt the information and verify the validity of the information within. HMAC-based token pattern uses a similar principle, but instead of encryption, you'd use a hashing algorithm. If token-based approach doesn't work for you for some reason, you might want to consider one of the security defense mechanisms. With double submit cookie, you would pass in the same pseudo-random value both in the cookie and in the request body. And the server would verify that both are equal. And if they're not equal, the server would reject the request. This relies on the same origin policy implementation of the browser, which disallows cross-origin requests to read responses from the server and also to modify cookies. With referrer header check, the server would enforce that the referrer or the origin header, if they are present, the values to be equal to the target origin of the request. Thereby, you're checking for cross-origin nature of the request. A similar check can be done by the browser itself. That is the same site cookie attribute. If that is set as strict, the browser will not send cookies in a cross-domain request context. The defense in depth techniques that are listed here have some flaws. They're easy to circumvent. So it is always best to use one of the token-based approaches for best security. Most developers would ignore login forms for CSRF, thinking that it will not apply there since the session is not established at that point. That is false. Login forms are also vulnerable to CSRF, just that the impact and risk view is quite different from the general CSRF case. This is an example scenario. Here, the victim is trying to load a page that has a CSRF attack code. The CSRF attack code in this case consists of a form that submits itself to Google, and it has the credentials of the attacker to log in. So once the victim has loaded this page, the victim has an authenticate session with Google on behalf of the attacker. And whatever the victim does going forward with Google, the history is logged into the attacker's account. So effectively, the attacker is spying on the victim without the victim realizing it. Again, the techniques for fixing this are very similar to the general CSRF case, but just that you should make sure to extend those techniques to cover the login forms. Let's wrap up with some recommendations. Before you even embark on fixing or adding protection, CSRF protection for your website, it is always best to make sure that no GET requests are mutable. If you do have GET requests that change state on the server, you are really violating the HTTP spec. And making GET requests immutable also makes life easier with CSRF because then you do not have to worry about passing tokens for GET requests. It is also a good idea to look for framework and library support for CSRF protection because most modern web application frameworks have some level of support. If you do not find any such help, you might want to consider implementing one on your own using one of the techniques that we discussed earlier. Finally, CSRF defense presumes there are no cross-site scripting vulnerabilities on your site because once you have such XSS holes, then no matter how much CSRF protection you add, it's of no use because at that point, the attacker could get hold of the token and hack into your website. Let's wrap up with a demo. So for the demo, I have a simple form that posts to the local server. And I will show how the post request from the local host works, whereas the same code that is hosted on a different domain would be rejected because it's of cross-origin in nature, and I have CSRF enabled in this code. So this is the page that does a simple post. I just put a message. So it's showing the token that is being used. And this is the same code that is hosted on a different domain. So now the request gets rejected with an invalid CSRF token message. For this demo, I'm using a Node middleware called CSRF. It's easy to get started with. You just install it like any other node module. And the middleware itself provides two capabilities. One is to provide a way to create CSRF tokens, and also it takes care of validation of the tokens on the server side. So the middleware provides a method called CSRF token. It adds that method to the request object, and you just include that token in the form. That's what I'm doing here. I have a parameter by name underscore CSRF. That is one of the default places it looks for. There are other ways to configure this. For example, you can have the token as a request header. And that's it. Any questions? Okay, the question was, how did CSRF get out of the top 10 list? I did read about it a little bit. It seems like this is more of going into the plumbing side of things, meaning more and more frameworks and libraries are taking care of this automatically. Just like what happened with SQL injection attacks, most developers won't worry about it today because most libraries, even React, for example, takes care of that automatically. So it's going under the covers. So most libraries tend to do this automatically. Um, yeah, this becomes important with legacy applications where you don't have such privilege of getting access to newer code, newer libraries, where such implementation becomes, it matters. Right. Yeah, it's more of the plumbing. It's going into, below the covers. Thank you.